All right, let's start. So today we are going to learn the last testing technique we are going to learn for this course. And because next week we are going to learn some algorithms which could be used for testing and even some other scenarios. But as for testing techniques, this is the last one to learn for this term and for this course. So the last one we are going to learn is combinatorial testing and when to stop testing. So today's outline is pretty straightforward. Sorry. The outline is pretty straightforward. We are just going to learn combinatorial testing, and then we are going to learn about when should we stop testing. So first, let's have a look at combinatorial testing. So in the name of this technique, we can see the keyword here is like combinatorial or combinations, right? So let's think about combinations. So in this example function here, which is actually from the last question of assignment 1, we can see that these are the test cases we were trying to evaluate, right? So these test cases could be viewed as combinations of values of different parameters for this function, right? So we can see there are some combinations here. So we are combining different possibilities of parameter values to make test cases. So this is the first type of combination we can see here. And another scenario where we can often see combinations in software is like something like this. So we can see that there are a lot of GUI items, right, when we are trying to use software. And inside the GUI of this software, we have a lot of fields for us to input something there. So these are also where we can have combinations, right? We can have combinations of different names, different emails, and different phone numbers. So we can have combinations of input parameters. So this is what we can have. And let's think about more combinations we can have from software. So in this example here, if you can't see it clearly, I can read it for you. So this is local group policy editor, so which is a policy editor for different groups of users. This is a setting for Windows operating system, and you can see that we can configure different rules and policies here through this, and we can actually build combinations of. I'm not controlling the light, but I don't know why it keeps turning on and turning off here, but yeah. So this is another type of combination we can observe here. So we can have different combinations of different policies. And when we try to click on some configuration items of, for example, Windows, we can also see some system configurations. So we can have, you can see these radio buttons here and these check boxes here. You should notice the difference between radio buttons and check boxes because this is also useful for your quizzes. If you observe for check boxes, it means that there might be more than one correct answer, right? And if you see radio button, then it means that there's only one correct answer. So you can see, but let's come back to this configuration here. So you can see that we can have different combinations of different settings here as well. So the second source of combination is like the configuration options of the software, which are not directly user inputs or input parameters, right? They are kind of different. So we can have different combinations to test the behavior of that could affect the behavior of the system or the software we are trying to test. And the question here is, we can use these combinations to trigger different behaviors of the software, and we can use this kind of observation to do testing. But how can we systematically generate the combinations? Of course, we can just randomly combine different things, but we don't want to do things fully randomly, right? We want to systematically cover all or some representative combinations. So this requires us to do combinatorial testing. So if we want to systematically try out different combinations or different possibilities, we could do combinatorial testing. And this is the definition of combination testing. So combinatorial testing is actually a testing technique that tries to check all or just some combinations of the system inputs. So the most common application of combinatorial testing is to check different combinations of the user or the input parameters or the different configuration options of the system. And you can see that this is an example of different combinations of system options. You can see we can try out different operating systems, and we can try to combine different choices of operating systems, of browsers, of protocols, of CPUs. And you can see that from the browsers, you can see IE inside this list. This tells us that this table here is actually quite old, right? And you can make a guess how old it is. Can you make a guess? Like how old is this table here? You can see IE, but you can't see Chrome. Actually, this table is from the NIST report. I'll tell you what is NIST later. And, and they are the organization proposing the idea of combinatorial testing. And in this report, they first mentioned the term combinatorial testing. And this combinatorial testing was proposed by them like 20 years ago. So they did a study 20 years ago, and in that study, they proposed the idea of combinatorial testing. And combinatorial testing is also known as T-way testing, and we will learn why it is called T-way testing in the following up slides. And if you wonder what is NIST, why are they interested in creating some new testing techniques? Actually, NIST is a US department which is called the National Institute of Standards and Technology, because they want to have some guarantee of the quality of different techniques, and they want to provide some standards. If they want to provide standards, they have to have some evidence of the quality, right? So they are interested in investigating new testing techniques, and in this study, they proposed combinatorial or T-way testing. So now let's, given this definition and the rough idea of combinatorial testing, let's do a live poll. So which levels of testing does combinatorial testing belong to? You can you can scan the QR code if you haven't. And if you are done, let's get to the question here. So you can see the difference between radio buttons and checkbox again. So which levels of testing does combinatorial testing belong to? Just now we discussed combinatorial testing could be done for input parameters and system configurations, right? So which one of these levels have input parameters or system configurations or system options? Actually, all of them have. So let's see the result. I can't see who is doing it correctly here, or just from here, but actually, combinatorial testing can be. Sorry, I don't know why it's not full screen. If I get back, so combinatorial testing actually belongs to all levels. So for unit level, we can combine different input combinations of input parameters. For integration level, we can also have different combinations of input parameters, right? And maybe we can have some system configurations in integration level. And for system level, we have both input parameters and system configurations. And now let's think about another problem. What is the color of box for combinatorial testing? Is it black box or gray box or white box? What is the color here? So we just care about different combinations of input parameters or system configuration options. So what is the color of box? Yes, black box. Yes. So because we don't know the internals of the software we are testing, we don't have access to the source code, and it's also not gray box because we are not kind of instrumenting the software. We are not getting information from the code. So that's why it's totally black box. We are just dealing with different inputs. And now let's come back to the term T-way combinations. So just now we mentioned that combinatorial testing is also known as T-way testing. So what is the meaning of T-way here? Why do we care about this letter T here? So actually the goal of so T-way testing or T-way combinatorial testing, the goal here is to test the combinations of input parameters covering all the possible sets of parameter values for a specific integration level. So in interaction level, so because we care about combinations, different combinations of variables. So these variables or input parameters are kind of interacting with each other, right? And we can set a particular level of interaction between different things for us to combine, like the input parameters or the system configurations. So we can set an interaction level as our goal for testing. So the interaction level here is T. So we use the term T-way communication. And let's have a look at some examples of different levels here. So if we take the value, if T takes the value of 2, then it means that we are doing pairwise testing, which means that we try to create a test suite that can cover all possible pairs of input parameter values for this system, for the program we are trying to test. So we try to cover all possible pairs of any two parameters here. So this is the definition of two-way testing. And for three-way testing, we are trying to cover all the possible triples of the input values of the input parameters, the inputs. So it's like the combination. We are trying to cover all the possible combinations of 3 inputs in our test suite. So this is three-way testing. And four-way testing is like we are trying to cover all the combinations of 4 inputs and so on. So this is why it's called T-way combinations. And let's think about another problem, which is called combination explosion. So did we encounter explosion, this term here in this course before, in some lectures before? Can you still remember that? Did we encounter this term before? Like explosion in our previous lectures? No? I hope you can remember it. Actually, we have learned path explosion before, right? So when we are trying to explore different paths, execution paths of the program, we can extract from the control flow graph, right? And whenever we have loops, whenever we have branches, we could have the problem of path explosion. We could have too many paths for us to deal with when we are doing testing. So, so this is so explosion here means we have too many things to deal with, right? So it's similar here for combinations. So let's think about this scenario here. Let's consider that we have n parameters here, and we are trying to do two-way combinatorial testing here for these n parameters. And what is the number of combining these n things together, and we take two out of the n things at a time? So how many test cases, how many possibilities do we have here if we do two-way combination? So what is the maximum number here? No. This is actually some, I think maybe you have learned it in high school, like combinations and calculating combinations. Like we have n things, we take two out of them. So it's like Cn2, right? The value is, yeah. So the calculation is like this. So is Cn2, yeah, choose two out of n things, and we don't care about ordering. So if we care about ordering here, then then we don't need to divide the 2 factorial here. We divide the value of n factorial by this 2 factorial here. It means that we don't care about the ordering of the two things we are choosing. And this n minus 2, we divide the value of n minus 2 factorial. It means that we don't care about the ordering of the things we are not choosing, right? So this is how it is calculated. And this value, this value actually it equals to n times n minus 1. And can you imagine how that's n times n minus 1 divided by 2, sorry. So can you imagine how will the curve of this thing look like? Does it grow faster and faster, or does it grow slower when n becomes larger? Is it faster or slower? N times n minus 1 divided by 2 is growing faster, right? So you can, if we consider the x-axis as the value of n, then this is roughly how the curve looks like. So we will have too many pairs here if we have a lot of input parameters, and if we do, and this is only two-way combination, and if we do three-way combinations, we could have this curve will grow even faster, because it becomes n to the power of 3 something, right? If we do combinations of, if we do Cn3, so if the number of t grows up, if the number of t becomes larger, then we could have many more combinations to test. So this is a problem of combination explosion. So it becomes important for us to determine the value of t, because if we have a larger value of t, the combination explosion problem becomes more severe. So this is why we need to determine a suitable value of t. And and we want to set an upper bound of the value of t. So we don't need to test too many test cases. So this is the purpose here. And actually, we don't need to worry too much of determining the t to calculate a suitable t value on our own. NIST, their study has given us some answers. Actually, in their report, they found that most of the failures or bugs are caused by one value or combinations of two parameters. So you can see that from this graph here, this is actually from their report. So this interaction here means actually it's a value of t. It's a value of t. So you can see that they tested different types of software. They tested medical devices, they tested browsers, servers, and their distributed databases. And you can see that if we set the value of t to be 2, for most of the system, we can already cover over or maybe around 70% of bugs. So we don't need to, if we set the value of t to be 3, then we can cover maybe almost 90% of bugs for all the systems here. So normally we don't need to test the combination. We don't need to test for 4, 5, 6. So actually, because most of the failures, sorry, most of the failures are caused by only 1 or 2 parameters. So that's why we don't need to worry too much about having a larger value of t. So this is the finding from NIST. And actually, this can save us a lot of effort. Like it can reduce the number of test cases we need to have by 20 to 700 times. So now let's come to move on to another question here. So since we have already determined the value of t, right? So we know that, okay, how many what is the interaction level we want to have, and what kind of combinations we want to have. But then how do we generate the test suite becomes the problem. So do we just exhaustively generate all combinations with some, like when you were doing your assignment 1, when you do the equivalence class testing, you do the Cartesian product, right? You try to use for loops to combine everything together. So do we just exhaustively generate the combinations with some for loops, with some loops? So the short answer is no, because there are some redundancies and there will be too many test cases for us to handle, even if we just do two-way combinations, right? So instead, we try to use a concept called covering arrays. So covering arrays is a mechanism. It's actually some kind of mathematical structure to keep some information. But the overall idea of the covering array is that it can help us to keep track of what are the combinations, what combinations has been covered by the test cases, so that we can know that one particular test case could cover how many different combinations. So this is a basic idea. So it is, in general, it is just to help us to reduce redundancy. So if we try to define it mathematically, it is actually an n times k matrix. So n represents the number of test cases. So basically, each row is like in this covering array is like a test case. And each column here is actually the number of parameters. And each cell of this matrix is actually a specific value of that parameter. So this is the mathematical definition of covering array. And actually, if if we think about the real parameters the real things we are going to consider when we are trying to design test suites using for combinatorial testing, we need to introduce some more concepts here other than N and K. We need to introduce the concepts of T and V. So because when we are doing combinatorial testing, we want to limit the interaction level, right? So T here still stands for the interaction level. So if we set the T to be 2, it becomes pairwise. And if we set T value to be 3, we are trying to test the combinations of triples. And the V here, the V here means the number of possible values for each parameter. So this is to assume that, but this V here is just for us to do the, it is only for us to simplify the problem we are trying to think about here, because it has a very strong assumption here. So this assumption is actually very, very strong. So here, let's try to assume that each parameter has the same number of values. So which is often not the case in reality, but this could simplify the problem here. So let's assume that each parameter has the same number of possible values here. So covering arrays are very, very useful. So they can, like I just said, they can help us to reduce redundancy. So it can help us to improve efficiency because we have fewer test cases to deal with. Then we can do things faster, right? And it can also help us to ensure coverage. So we are reducing the redundancy, but we are maintaining the coverage of different combinations with the help of covering array. And then because we are reducing redundancies, so we can apply a higher value of T sometimes if we try to use covering array. And that's all about the definitions and benefits of using covering array. And let's use an example to see why it is useful. And let's use this example to practice the concept we have learned just now. So suppose we have this this covering array here. So we don't know, let's assume that for now we don't know the number of test cases we need. So N stands for the number of test cases, right? T, do you still remember the value of T? So T stands for interaction level, right? And K stands for the number of input parameters, right? So we have 4 input parameters. We have each parameter can take 2 values. And we are trying to do pairwise testing. So this is the meaning of this math notation here. And so how many pairs do we have here given this setting? So we have 4 parameters. We have 2 values. But we have 4 parameters here. And so how many pairs do we need to have? 6. I hear 6, and that is correct. So we have 6. So C42 is actually 6. So basically we have P1, P2, P1, P3, P1, P4, P2, P3, P2, P4, and P3, P4. So we want to cover all the possible value combinations for each pair here. And each pair can actually take 4 values, right? So for example, let's assume that each of the parameter can take only 0 and 1. So this makes things easier. So let's assume, so each pair can actually, take 4 values, like 0, 0, 0, 0, 1, 1, 0, and 1, 1. So how many test cases do we need to have if we want to generate test cases exhaustively? Is it 4 times 6? Is it 24? To exhaustively test, to generate the test cases. So we have 6 pairs, right? And each pair can take 4. Is it 4 times 6? Yes? Actually, no, it's only 16. Because 26 is kind of redundant. Because we have 4 values. We have 4 values. Each value, P1, P2, P3, and P4. And each value can be only 0 or 1, right? We can consider them as 4 bits. 4 bits. 4 bits, how many possibilities do we have for 4 bits? We have only 16. So it's 2 to the power of 4. Total number of possibilities we have. So if we want to test everything exhaustively, we only need 16. If we use 24, we will have some duplicate cases here. So we need 16 if we want to test everything exhaustively here. And this is without using covering array. So we are trying to, if we just do this, we need 16 test cases. But if we use covering array, we only need 6 test cases. And let's learn why do we need only 6 test cases. So this red dot here is actually a glitch with the animation of this page, but this page has a lot of animations. It's very, very hard to fix, and but we will see it doesn't matter that much. So let's assume that these are the 6 test cases we finally need to cover all the possibilities of all different pairs of combinations. And let's see why these 6 test cases can give us 100% of pairwise combination coverage. So remember we have 6 different combinations. So first, let's consider P1 and P2. So for P1 and P2, we need to cover 0, 0, 0, 1, 1, 0, and 1, 1, right? So we can use test case 1 to cover the combination of 0, 0, right? We can use test case 2 to cover the combination, the situation of 0, 1. We can use test case 3 to cover the combination of 1, 0, and we can use test case 4 to cover the combination of 1, 1, right? So we can use 4 test cases to cover all the possibilities for P1 and P2, right? And now let's consider the second pair, P1 and P3. So we can use test case 1 to cover the combination of 0, 0 for P1 and P3, right? So it's 0 here for P1, 0 here for P3. So we can use test case 1 to cover it. And then for 0, 1, we can use test case 2 to cover this situation for P1 and P3, right? And for 1, 0, we can use test case 4 to cover the combination of 1, 0 for P1 and P3. And for 1, 1, we can use test case 3 to cover. So now you can see that we can also cover all the 4 different combinations for P1 and P3. Let's consider P1 and P4 here. So for 0, 0, which test case do you think we can use? We can still use test case 1, right? Test case 1 is covering the scenario where P1 and P4 takes the value of 0, 0. And for 0, 1, which test case do you think we can use? Test case 2, right? For P1 and P4. And for 1, 0, which one do you think we can use? We can use test case 3. What about 1, 1? We can use test case 4, right? So we can cover all the possibilities of P1 and P4. And then let's move on, P2 and P3. So for P2 and P3, we can use test case 1 to cover the situation of 0, 0. And what about 1, 0? We can use test case, what about 0, 1, 0? We can use test case 3, right? For 1, 0, we can use test case 4. For 1, 1, we can use test case 2. What about P2 and P4? So for P2 and P4, we can use test case 1 to cover 0, 0. We can use which test case to cover 0, 1. So now, just now, all these 4 pairs could be, we can use the first 4 test cases to cover, right? So the first 4 test cases are enough to cover all the combinations for these 4 pairs. But for P2 and P4, for the case of 0, 1, we have to introduce another test case. So we need to use test case 6 to cover, to cover the situation of 0, 1. And for 1, 0, we also need another test case. So we need test case 5 to cover 1, 0 for P2 and P4. And then we can reuse test case 2 to cover 1, 1 for P2 and P4. And for P3 and P4, we can do the same thing here. We can see that we can use test case 1 to cover 0, 0. We can use test case 4 to cover 0, 1. We can use test case 3 to cover 1, 0. And we can use test case 2 to cover 1, 1. So basically, we only need 6 test cases here for us to cover all the pairs in this sample program. But then you may think, okay, this covering array looks like it's very useful, right? We can use this covering array to determine which test cases are covering which possibilities of combinations, right? So, but the question is, how do we get this array here? So we checked with this array that, okay, we can this is enough for us to cover all the possibilities, but how do we get this array from scratch? And it is actually not an easy problem. We have to use some advanced algorithms to calculate the covering array. So there are many research papers about how to calculate covering array effectively. And there are several algorithms. We have simulated annealing algorithm, and we have genetic algorithm. We will learn genetic algorithm later next week. And we also have some simpler algorithms called greedy algorithm. You might have learned it in some other courses. And let's learn how to use greedy algorithm to solve this problem here, because it's a relatively simpler algorithm. So we like to be greedy. So the process of greedy algorithm is to iteratively select test cases that can bring us, based on the current situation, that can bring us the most number of covered combinations at each step. So at a certain step, we may already have some test cases, and we might have already covered some combinations, right? And for the next step, when we are selecting the test case, we just select the one that can bring us the most number of combinations to be covered. So this is the basic idea of greedy algorithm. So it's very, very simple. So you just look ahead by one step. So assume that let's reuse the problem the example we used just now. So let's assume that we have 4 parameters A, B, C, and D, and we are trying to do two-way combinations, and each value can take 0 and 1. So the first step is we can just start from a random test case. Let's say that we are trying to use the test case of all zeros. So this is a test case 1 we have, and this is the covering array. So we are trying to build, and this is the table to keep track of the covering of all 6 combinations. So we have 6 combinations to cover, right? So we can see that this test case is enough. So this test case is actually enough to cover all these 6 different combinations here in this scenario. So now let's do step 2. So we have 6 pairs of input parameters for us to try to cover, right? So given this test case, given this existing test case, can we come up with another test case that can cover all the 6 pairs, that can bring new combinations for all 6 pairs? So we need to think about this problem in this step. So the short answer is yes. So the test case we can find is something like this. So it's like 0 for A and 1 for the rest of the values. So in this case, we can use this test case to bring in 6 more combinations for all 6 pairs. So now, what do we need to think for step 3? We need to think about the same thing here, right? So we need to think about the same question here for step 3. So can we come up with, given the situation like this, so we have the covering array like this, we have the covered pairs like this, so can we come up with a new test case that can cover all 6 pairs? So in order to cover 6 pairs, we have to make sure that so when we think about this problem, we can break down this solution step. So since we already have 0, 0 and 0, 1 for A and B, right? We need to think about 1, 0 for A and B, right? Because otherwise we are repeating the value of A and B, right? So we have to use 1, 0. And since we already have 0, 0 and 0, 1 for A and C, so it's better we think about covering 1, 0 for A and C, right? And so on. So we can break down the problem of checking whether can we find the optimal test case with by breaking down this problem. And the short answer of this question at this step is actually no. We can't find such a pair. So if we take the value of C to be 0 here, we are repeating 0, 0 for BC. If we are taking the value of C here to be 1 here, then we may repeat the value of some other things. So let's assume that we take this test case 3 here. So this can give us actually new pairs for 5 test cases. For B and D, it cannot give us a new combination. So this gives us 5 more combinations or patterns, and we can repeat the process So we can try out the case where A and B takes the value of 1 and 1. And then we determine the rest of the values accordingly. So eventually we can get this covering array, and we can get everything inside this table covered. So we can cover all the possible combinations, and we can build this covering array. So this is roughly the idea of the greedy algorithm. And for each step, when we are trying to deal with the problem here, if we want to write a program to automate this, you can think about, okay, can we find a pair test case that can introduce 6? If the answer is no, then we think about, can we bring up a test case that can help us to cover 5 new pairs? And if no, then we think about 4 and 3 and 2 and so on. So this is how you can roughly write a program to reflect this greedy algorithm process. So there are some pros and cons for this algorithm for using this algorithm to calculate covering array. So the advantages are, so first, it's very fast because you can see that we only look ahead one step, right? So we don't need to do too much of computations. It's very fast and it's quite practical. And it can provide us near optimal test suites. So this is the advantage. However, there are some limitations for this algorithm as well. So it may not produce the smallest possible covering array because, like most of the greedy algorithms, it doesn't provide us the global optimal solution here. So especially when we have larger value of t or more complex combinations of input values. Just now, the input parameters can only take 2 values per parameter, right? If we can take more values, and if we have a larger value of t, then this greedy algorithm is more likely to give us a non-optimal solution. And for those higher order of t or more complex cases, some meta-heuristic methods may give us a smaller test suite. So that's all about the limitations and advantages of this greedy algorithm, and let's think about the limitations of combinatorial testing. So the first one is the parameter explosion problem. So there could be a lot of, just now we did a simple calculation of the potential combinations we could have. So the challenge could be managed by selecting a lower level of t. And another problem is there could be constraints in between parameters, input parameters. Some input parameters are not practically meaningful if we combine them together. For example, you can still remember the radio button, right? So if we combine if 2 values are kind of exclusive, so we can have either one of them, but it's not meaningful to put both of them together in our test case, right? So there are some meaningless combinations. So due to the constraints of maybe the constraints could be semantically derived. It could also be written in the code. So there are some constraints for the input parameters, which will make some of the combinations not feasible or meaningless. And the last limitation is like combination testing is good at detecting the faults because we are trying to deal with combinations of different combinations of different input parameters. So most of the bugs we can find with combination testing are likely to be the interactions between different parameters or different configuration values. So this may lead us to miss certain types of bugs. For example, those bugs there could be some bugs not related to the interactions between input parameters, right? There could be bugs related to the program states. So in that case, we may miss some bugs with combinatorial testing. So that's the last limitation here. And that's the first half of today's lecture. And sorry, let's have a 10 minutes break. And I'll see you at 12:05. Okay, let's start the second half of today's lecture. So the second topic we are going to cover is when to stop testing. So, because like I just mentioned, combinatorial testing is the last testing technique we are learning for this course. And now let's think about when to stop testing. So we have learned many testing techniques or many testings so far. So I learned functional testing, right? Black box testing is all about how do we divide the space, the input space. We can use boundaries to divide. We can use equivalence classes to divide the input space. We can use the cause and effect relations to divide the input space. And then we learned non-functional or white box testing. So white box testing is all about different types of coverage, right? So we have statement coverage, we have branch coverage, path coverage, and def use coverage, which is related to data flow. And we learned gray box testing, which is we will be practicing it using fuzzing for segment 2. And then we learned different levels of testing, for example, unit testing, integration testing, and system testing. And we also learned some test oracle related types of testing, for example, differential testing, regression testing, and metamorphic testing. So these are test oracle related. And then we learned mutation testing. Although it is called testing, it is actually some technique to evaluate other testing techniques. So we have learned many testing techniques and concepts so far. And just now we learned one more, combinatorial testing. And now, so we can see that, okay, testing is everywhere here in this course. So, but the question is when should we stop testing? So is it another type of testing called when to stop? It's actually no. So maybe after this term, you can stop testing. After taking this course, after finishing assignment 2, you can stop testing. Is that the case? So I hope it's not, because when you go to work, you still need to write test cases. So in practice, when to stop testing is an important thing we should think about, because for a company to release the software, we have to do some kind of testing, but we can't test forever, right? We have to have some stopping criteria for us to do testing. So the question is about how should we know when we are done? So we can use several different metrics for us to set the stopping criteria here. So first we can use the requirements. So we can write tests based on the requirements. And when all the tests according to the requirements can pass, then we can stop testing. And we can also set some metrics of using coverage. For example, if we can achieve maybe 90% of statement coverage, then we stop testing. Or we can use budget. So when we don't have time to do testing, then we just stop. Or when we don't have money to support to do testing, then we stop. So you can use budget as well. Or we can use plan. So plan is similar to budget. So basically we just stop according to the plan or budget. And then, but the ideal case is to somehow measure the dependability of the software. So if the software is dependable enough, then we stop testing. So remember, software dependability is actually a concept introduced all the way back in lecture 1. So software dependability is actually made up of correctness, reliability, safety, and robustness. So let's have a quick recap of all these 4 concepts. So For correctness, a program is correct if it is consistent with its specifications. And for reliability, it is a measurement for the likelihood of behaving correctly during the observed period of time. And for safety, it is the ability to avoid some hazards. And for robustness, is that the software can gracefully handle failures. So this is robustness. So let's think about which one of the property here could best represent software dependability in the context of testing. So we need to somehow measure the dependability, right? We need to somehow extract some values or some statistics out of these qualitative measurements. So we want to do things quantitatively to calculate, to make these metrics countable. So we have learned that finding all faults is nearly impossible because the program could have infinite number of states, and we could have infinite number of test inputs, and we could have infinite number of scenarios. And even if a piece of software can work correctly according to the requirements today, it may not work tomorrow because the requirements might change as well, right? So it's almost impossible to find all faults, and it is too expensive to find all faults. So this means that we can always test more. So we must establish some criteria for us to stop testing, to make sure to tell that okay, the system is dependable enough. So let's think about these four characteristics according to this context here. So correctness is hard to actually prove unless we do some kind of formal verification, right? So it's hard to use. Robustness or safety are quite important, but they are not enough. So they are only representing a specific aspect of the software. Safety is more related to avoiding hazards, and robustness is more related to handling failures gracefully, right? They are important, but they are not enough. And so the most usable metric here is actually reliability. So it's actually the basis for arguing dependability here. So let's think about how can we derive some metrics according to reliability. So reliability is like the probability of failure-free operation or behaving without any failures for a specific observed amount of time in a specific environment. So this means that reliability actually depends both on the system and the users. So if the users are kind of malicious users like hackers, then this software may not seem to be very reliable. However, if the users are just normal users, then the reliability could be observed differently, right? So this is more like a formal definition, and informally, so it's like reliability is like measuring how well the users think about this system, providing the services, how well the system can provide the service they require. So reliability is improved when the system, so when the faults, because it's related to the user, both user and system. So it depends on the usage pattern. And if the faults in the most frequently used parts of the system are removed, then we can greatly improve the reliability, right? So, however, removing a particular percent of faults does not necessarily lead to improvement exactly to be the same number here for reliability. And actually, in a study, researchers have found that removing 60% of the faults actually only led to a 3% of reliability improvement. So this is roughly the case. But after all the discussion here, like the definition and how it can be improved, actually what we can get here is reliability can be defined and measured, so it could be turned into some kind of metrics. So the first metric we can get from measuring reliability is the probability of failure on demand. Sorry. So this is actually, you can, this, the calculation of this is actually the name of this metric is actually self-explanatory. So we know how to calculate this metric, the value of this metric from its name actually. So it's basically the probability of failure, right? On demand means per request. So on demand means is requested from the user. So it's like failure per request, basically. So it is calculated as the number of failures divided by the number of requests over a period of time. So this is an example. If we have this probability of failure on demand value equals to 0.001, it means that 1 out of 100 service requests result in a failure in that observed period of time. So it should be, so this metric should be used in situations where the failure on requests is serious. So it's because this value here is independent from the frequency of requests. So it doesn't care about how frequently the user would request the service, right? It just cares about how likely a request would end up in a failure. So it's independent from the request frequency. And although you may think that, okay, this 1 out of 1,000 requests sounds very dangerous, right? Or very risky. But let's assume that if this service is only used like 100 times during its entire lifetime, then this 1 out of 1,000 failure rate is not that bad, right? So this is the case. It doesn't care. So it doesn't care about the frequency of how frequent the requests are used. So frequency is, so if we want to deal with frequency, we need to think about time, right? And this gives us, if we think about time, this gives us the second metric here, availability. So availability means during a period of time, how much of time is the service available to the user? So how much of the time does this service run without an error? So this is calculated by using the uptime divided by the total time running this service. So we should take repair and restart time into account. So this repair and restart time are considered as downtime, not uptime. So if the system is restarting, then it's still considered down. So, and we don't care about incorrect computations or partial failures. So it means that if the system gives us some wrong answers in some particular cases, but it's still running, then it's still considered as available. So we don't care about these kind of partial failures. We only care about the situations where the entire system is not available, is down. So let's say we have this availability of 0.9999. It means that this system is available 99.99% of time, And to give you a feeling of how this availability feels, it's like every day the 0.9 means every day the system is down for like 144 minutes. So that's over 2 hours. So 0.9 availability is actually not that good. 0.99 is like the system is not available like every 15 minutes. And 0.99 means the system is not very available for like 84 seconds. And 0.99 means only 8.4 seconds is not available each day. So this is roughly how does it feel in our daily life. And another metric related to the frequency of request is the rate of occurrence of fault. So this name is also self-explanatory. So basically it calculates the rate or the frequency of errors during a period of time. So this rate of occurrence of fault, if the value is 0.02, it means that there are two values in 100 time units. So this is the idea here. So this metric is useful when the requests are made on a regular basis. So it means that it doesn't care about the count, the number of requests. It's only related to the time. So this is useful when the system is receiving requests constantly. So another metric related to this the time-based failure is mean time between failures. So mean time between failures is like it's basically the average length of time between two observed failures. Like if we want to calculate this mean time between failures, we need to keep track of the timestamp where each failure happens. And mean time between failures of 500 means that the average time between two failures is like 500 time units. So like just now we learned there are many metrics to we can use to reflect the reliability of the system, and in order to collect values, to calculate the values of these metrics, we have to collect data from the user sessions, right? We have to make observations by running the system, right? So we have to capture some data here. And these are the data we could capture. So if we measure the number of failures per given number of requests, then we can use it for the error per request metric, right? And then if we capture the number of failures with regard of the time, then we can use the time-related metrics. And if we capture the timestamp, we can use this mean time between failures metric. And let's use an example to learn about these different metrics. So let's assume that we have 10K requests, and we have 35 run results, and we have 5 requests that are crashes. So what is the probability of failure on demand here? So we can't, because we only have the information about the number of requests and the number of failures. We don't have the information about the time, right? We can't use the time-related metrics. We can only use the probability of failure on demand. So what is the value of this one here? Actually, both run result and crash should count here. because we are not dealing with availability. And so we should care about all types of faults. So we just need to use 35 plus 5, which is 40, divided by the total number of requests. And that is very, very simple. And let's consider another scenario. We run the software for 144 hours. And during this 144 hours, 6 million requests have been made. And the software failed on 6 requests. So what is the rate of occurrence of fault here? What is the probability of failure on demand here? And what is the mean time between failure here? So let's first consider the rate of occurrence. Because we have time information here, we can use the time-related metrics. So let's first consider the rate of occurrence of fault. So rate of occurrence of fault is actually how many faults per time unit, right? So we have 6 requests and 144 hours. Basically, we just use 6 divided by 144. Sorry. So it means that the rate of occurrence of fault is 0.04 per hour, since the time unit is hour here. And what is the rate? What is the probability of fault on demand, failure on demand? So we should use. We have 6 fails, right? 6 failures, and we have 6 million demands. So we just use 6 divided by 6 million, and that is 10 to the power of minus 6. And what is the mean time between failures? So if we want to calculate it accurately, we should use the information of timestamp. But if we just want to briefly estimate this value here, we can simply use the total number of time divided by the number of requests. So basically, it's around 24 hours per failure. And let's continue. So let's assume that a piece of software has a rate of occurrence of fault of 0.001 failures per hour. So, however, it takes about 3 hours on average to get the system up again after a failure. So what is the availability per year? So how do we calculate this? So first we need to calculate how many errors or how many failures could we have per year, right? According to the definition. So every year we have approximately 8,760 hours. And then if we use this many times and this rate here, we can get this system may have 8.76 failures per year. And then let's calculate the downtime, right? The downtime is 3 hours per failure. So it means that we have like 26.28 hours of downtime per year. So we basically just use the total number of time per year minus the downtime, that is the uptime, divided by the total time per year. So the availability of this system is about 0.997. So this is the availability of the system here. So as we can observe, we can use these metrics to do a lot of calculations, and we can actually do some statistical testing with these metrics. So rather than like using the test cases to trigger failures to find bugs, we can actually also use test cases to measure the reliability, right? By running the system and observing for failures during a period of time. However, because we know that reliability is related to both the system and how the user would use the system, so in order to reflect the real reliability in real scenarios, we need to make sure that the test inputs we have here could actually reflect the usage patterns or the usage profiles of users. So this is the first thing we need to consider here. And then when we do this, when we do this testing for reliability, then we can record errors and other measurements. For example, the timestamps for errors. Then we can calculate the different metrics. And then we can set an acceptance level of reliability according to these metrics. And once the metrics reach, or the reliability metrics reach certain level, we can stop testing. So this is the basic idea here. So here, the key thing here is about how do we capture the operational profile? How do we know that, okay, this system is performing like what's happening in real life? So for the operational profile, we want to reflect how the software is actually used in real world, and it should consist different types of inputs, and different types of inputs should occur in the similar probability as their occurrence in real life. For example, in real world, when we do testing, normally if our purpose is to try to find bugs, we try to use corner cases, right? But if we are trying to evaluate the reliability of the system, we shouldn't just care about the corner cases. That's because in real life, people are most of the time people are using the normal use cases, right? They don't use corner case inputs in real life. So when we are trying to test for reliability, we should make sure that our the probability of appearance of different classes of inputs should be similar to how the system is really used in real life. So this is the idea here. And this operational profile could be specified in advance if we can get some hints from other similar systems. And for new systems, it's hard for us to determine because we don't have usage data, right? We don't know how would users use this system. So what we can do is we can conduct beta testing, which is to release the software to a group of users and let that group of users to use the system for a while, so we can collect their usage patterns and then we can generate test cases similar to their usage patterns. So this is the idea. But we should keep in mind that the usage may change over time. For example, different user groups could use our software later on, right? So the usage pattern could change. So this is something we should keep in mind. And the procedure of doing this is like this. So we should study the existing systems or doing some beta testing to collect the user usage pattern, and then we can form an operational profile like we just mentioned. And then we can construct test inputs that can reflect this profile. So basically, with the operational profile, we roughly know that, okay, how many % of the user inputs are related to which part of the code, right? Which part of the system. So we can construct test inputs roughly similar to the operational profile, and then we can test the system with the constructed test inputs, and then if once we have observed some number of failures, then we can calculate the reliability. So accordingly, using those metrics. So these are the 4 steps. So this can help us to estimate the reliability without actual users. So, but this requires the operational profile to be as realistic as possible. However, there are some limitations of doing this kind of statistical testing for reliability as well. So because as we could see from the procedure or the definitions, this operational profile is the key here. So if we cannot get a very high quality profile, then the result of this statistical testing may not be trustworthy. So, and this profile could change over time as well. So there could be high cost of generating test inputs here as well, because if we want to simulate the real world usage, we may need a large volume of test inputs. So this could be expensive to generate. And there could also be some statistical uncertainty. So for example, we may not encounter enough number of failures to make sure that the metrics are calculated with statistical significance. So this may give us some uncertainty here. So in this case, we don't know whether the system is already very reliable so that it's free from bug, or it's because we didn't have a good set of test case, right? So because we observe no bugs. So this could also cause some uncertainty here. However, normally when we do statistical testing and we are improving the systems according to our testing results, this is the failure rate or the different metrics values of related to reliability should look like this. So the failure rate should drop, and when we observe the failure rate to be lower enough, we can set a stopping point. So we can stop testing when the failure rate is low enough. So although it has many limitations, and it could help us to provide to observe the failure rates of the system, to observe the reliability of the system, and once we think that the system is reliable enough, we can stop testing and release the software. And that's it for today's lecture. And so once we think that you are equipped with enough knowledge about testing, then we can stop testing here. So it's similar to the logic of this course. And before we actually end today's lecture, let's have a very quick recap of what we have learned just now. So basically today we learned two concepts: combinatorial testing and when to stop testing. So for combinatorial testing, we learned that we can combine different input parameters, we can combine different system configurations, and combinatorial testing is also known as T-way combinatorial testing, right? And the keyword T here means the interaction level. And normally, according to the report of NST, we only need to do a 2 or 3-way combination. However, even when we do combinatorial testing, we may have some redundancies, and we can remove these redundancies using the covering array. But constructing the covering array is not simple. We can use the greedy algorithm to construct covering arrays. But the drawback of using greedy algorithm is that the calculated covering array may not be the global optimal. And that's about combinatorial testing. And we also learned when to stop testing. And when to stop testing is determined by whether the system is reliable or dependable enough. And we have several metrics for calculating the reliability of the system. And all of them are actually related to failures, but some of them are related to failures per request. Some of them are related to failures per time unit, right? So, and availability is a special one. It's only about the uptime divided by the total time. So these once we know these metrics, we can try to build some operational profile of the system and do statistical testing to get the value for these metrics and to estimate the reliability of the system, so we can tell when to stop testing. And that's it for today's lecture. And thank you for coming on Friday. Thank you, and have a nice weekend.